When we talk about large language models, pre-training gives them their broad competence, but fine-tuning is what makes them useful for specific tasks. Fine-tuning is the process of taking a pre-trained model and adapting it to a narrower domain or a particular application. It is the stage where general linguistic knowledge is aligned with specialized requirements. Without fine-tuning, a model would remain a generalist, capable of producing fluent text but not optimized for tasks like legal analysis, medical diagnosis, or customer support. With fine-tuning, the model becomes a specialist, able to apply its general knowledge in ways that meet the needs of a specific context. Fine-tuning works by continuing the training process, but on a smaller, task-specific dataset. The pre-trained model already has billions of parameters shaped by exposure to massive amounts of text. Fine-tuning adjusts those parameters slightly, nudging them toward patterns that are relevant to the target domain. For example, if the task is sentiment analysis, fine-tuning teaches the model to pay more attention to emotional cues in text. If the task is legal reasoning, fine-tuning teaches the model to prioritize statutes, precedents, and formal language. The adjustments are relatively small compared to pre-training, but they make a significant difference in performance. There are different strategies for fine-tuning. One approach is full fine-tuning, where all parameters of the model are updated during training on the new dataset. This provides maximum flexibility but requires substantial computation and can risk overfitting if the dataset is small. Another approach is partial fine-tuning, where only certain layers or components are updated. For example, one might freeze the lower layers of the transformer, which capture general linguistic features, and fine-tune only the upper layers, which capture task-specific features. This reduces computation and preserves general knowledge while adapting the model to the new task. A more recent strategy is parameter-efficient fine-tuning. Instead of updating the entire model, small additional modules are inserted into the architecture, and only these modules are trained. Techniques like adapters, low-rank adaptation, and prefix tuning fall into this category. Adapters are small neural networks added between layers, which learn task-specific adjustments. Low-rank adaptation modifies weight matrices with low-rank updates, reducing the number of parameters that need to be trained. Prefix tuning prepends learned vectors to the input sequence, guiding the model's attention without changing its core parameters. These methods allow fine-tuning to be performed with far fewer resources, making it accessible to organizations that cannot afford full retraining of massive models. Fine-tuning also interacts with data quality and size. The effectiveness of fine-tuning depends on the relevance and representativeness of the dataset. If the dataset is too small, the model may overfit, memorizing examples rather than generalizing. If the dataset is too narrow, the model may lose its general competence. Balancing specificity and generality is a key challenge. In practice, fine-tuning datasets range from thousands to millions of examples, depending on the task. Careful curation is essential to ensure that the model learns the right patterns without inheriting biases or errors. One of the remarkable outcomes of fine-tuning is transfer learning. Because the model has already been pre-trained on vast amounts of text, fine-tuning requires far less data than training from scratch. A model that has seen billions of tokens can adapt to a new task with only a few thousand examples. This efficiency has revolutionized natural language processing, making it possible to build specialized models quickly and cheaply. It also enables rapid experimentation, where models can be fine-tuned for different tasks and compared without massive resource investment. Fine-tuning can be supervised or unsupervised. In supervised fine-tuning, the dataset includes labeled examples, such as sentences tagged with sentiment or questions paired with answers. The model learns to map inputs to outputs based on these labels. In unsupervised fine-tuning, the dataset may consist of raw text from a specific domain, and the model continues training on the language modeling objective. This helps the model adapt to the style and vocabulary of the domain, even without explicit labels. Both approaches are useful, and often they are combined. Another dimension of fine-tuning is alignment with human preferences. Beyond task performance, models must produce outputs that are safe, helpful, and aligned with human values. Techniques like reinforcement learning from human feedback are used to fine-tune models in this way. Human annotators provide feedback on model outputs, indicating which responses are better. The model is then trained to maximize reward based on this feedback. This process aligns the model's behavior with human expectations, reducing harmful or unhelpful outputs. It shows that fine-tuning is not only about technical performance but also about ethical and social considerations. Fine-tuning also enables multilingual adaptation. A pre-trained model may have general competence across languages, but fine-tuning on a specific language or dialect improves performance. This is especially important for low-resource languages, where pre-training data may be limited. By fine-tuning on domain-specific corpora, models can become effective tools for translation, summarization, or information retrieval in languages that would otherwise be underserved. In code models, fine-tuning adapts general language knowledge to programming languages. A pre-trained model may understand syntax and semantics broadly, but fine-tuning on repositories of code teaches it specific conventions, libraries, and idioms. This enables tasks like code completion, bug detection, and automated documentation. It demonstrates that fine-tuning is not limited to natural language but extends to formal languages and technical domains. Fine-tuning also supports personalization. By fine-tuning on data from a particular user or organization, models can adapt to specific styles, preferences, or workflows. For example, a customer support model can be fine-tuned on transcripts from a company's interactions, making it more consistent with the company's tone and policies. A writing assistant can be fine-tuned on an individual's past work, making its suggestions more aligned with their style. This personalization shows the flexibility of fine-tuning, though it also raises privacy concerns, since personal data must be handled carefully. The future of fine-tuning involves scaling and efficiency. As models grow larger, full fine-tuning becomes impractical. Parameter-efficient methods are likely to dominate, allowing adaptation without massive resource use. Researchers are also exploring continual fine-tuning, where models are updated incrementally as new data arrives. This would make models more adaptive and current, reducing the problem of outdated knowledge. Another direction is federated fine-tuning, where models are fine-tuned on decentralized data sources without centralizing the data. This could improve privacy and security while still enabling adaptation. Ethical issues arise with fine-tuning as well. If the fine-tuning dataset contains biased or harmful content, the model may amplify those issues. If fine-tuning is performed without transparency, users may not know how the model has been adapted or what limitations it has. Responsible fine-tuning requires clear documentation, careful data selection, and ongoing evaluation. It also requires consideration of who controls fine-tuning and for what purposes. A model fine-tuned for propaganda or disinformation could be harmful, while a model fine-tuned for education or healthcare could be beneficial. The same technique can be used for very different ends. From a systems perspective, fine-tuning interacts with deployment. Organizations must decide whether to fine-tune models themselves or rely on pre-trained models provided by vendors. Fine-tuning requires expertise, data, and resources, but it provides control and customization. Using vendor models may be easier, but it limits flexibility. Hybrid approaches are emerging, where base models are provided and users fine-tune lightweight adapters. This balances efficiency with customization, making fine-tuning more accessible. As we conclude, it is clear that fine-tuning is the stage where large language models become practical tools. Pre-training gives them general competence, but fine-tuning aligns them with specific tasks, domains, and values. It involves adjusting parameters, adding modules, and training on curated datasets. It enables transfer learning, personalization, multilingual adaptation, and ethical alignment. It raises challenges of bias, privacy, and sustainability. And it continues to evolve toward efficiency, continual learning, and federated approaches. Fine-tuning is the bridge between general intelligence and applied intelligence, the process that turns broad capability into targeted utility. Without fine-tuning, large language models would remain impressive but unfocused. With fine-tuning, they become versatile tools that can serve diverse needs across domains, industries, and societies.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.